This is not just a train. It is a 600-ton metal spear, fired across the landscape at over 400 kilometers per hour. It moves so fast, it literally creates sonic booms when exiting tunnels. At that speed, the slightest imperfection, a tiny bump in the track, a gust of wind, a curve that's a fraction of a degree too sharp, should be catastrophic. It should send this behemoth flying off its rails into a billion pieces. And yet, it doesn't. Why? The answer is far more complex and brilliant than you think. It's not just about wheels on a track. It's a symphony of hidden engineering marvels designed to conquer impossible challenges. Today, we're dissecting two titans of trains, Japan's legendary Shinkansen and the futuristic, floating Maglev. We'll uncover the secrets that keep them glued to their path. This isn't just about trains, it's about mastering physics itself. Let's start with the Shinkansen, the train that started it all. If I asked you how it stays on the track, you'd probably point to this, the flange. But here's the secret: at 320 kilometers per hour, if this flange is constantly grinding against the rail, you're not on a high-speed train, you're on a high-speed disaster. The friction, the noise, the wear, it would tear itself apart. The flange is just a last resort safety measure. The real genius is in the shape of the wheel itself. Your car's wheels are flat cylinders. A Shinkansen's wheels aren't flat. They're slightly conical, like a cone with the top chopped off. This is called wheel profiling, and it's an incredible self-correcting system. If the train drifts, say, to the right wheel rides up onto its wider diameter, while the left wheel simultaneously shifts to its narrower diameter. Since the wheels are fixed on an axle, they have to rotate at the same speed. But the wider part of the right wheel now has to travel a greater distance per rotation than the narrower part of the left wheel. This difference in distance naturally steers the entire axle back to the center of the track. It's constantly making tiny, automatic corrections, without the flange ever needing to touch the rail most of the time. It's a principle called hunting oscillation, perfectly tamed by precise engineering. If you're enjoying these kinds of deep dive engineering breakdowns, take a moment to subscribe so you don't miss our next one. Alright, now on to the track itself. A perfect wheel is useless on an imperfect track. The foundation of the Shinkansen's stability is its path, hermetically sealed from the rest of the rail network. Ordinary tracks, with gaps and wooden sleepers on loose gravel, would make a high-speed train vibrate itself to pieces. First, the rails are continuously welded, kilometers of seamless steel, eliminating the classic clickety-clack and the vibrations that come with it. Second, many sections use slab track, where rails are fastened directly to solid, reinforced concrete beds. It's monstrously expensive, but it provides the rigid, unwavering stability these speeds demand. The tracks are designed to be as straight as possible, with incredibly gentle, wide-radius curves. Turning? A sharp curve at 300 kilometers per hour is impossible. These curves have a minimum radius of 4,000 meters. To put that in perspective, a simple 90-degree turn would stretch over 4 kilometers of track. And instead of narrow gauges, the Shinkansen uses a wider, standard gauge for greater stability. But a system this precise needs an equally precise way to stop. A 600-ton train moving at 320 kilometers per hour carries terrifying momentum. Conventional friction brakes, like the ones in your car, would burn to scrap metal. So the Shinkansen relies on a multi-layered braking philosophy. The primary brake isn't even a brake at all. It's the motors running in reverse. This is regenerative braking. The train's momentum forces the electric motors to act like generators, converting kinetic energy back into electricity, which can even be fed into the grid. It's incredibly efficient and does most of the work, slowing the train smoothly without ever touching the wheels. For extra stopping power, there are electrically controlled air brakes with precision disc systems. But in a true emergency, some Shinkansen series deploy eddy current brakes. These are powerful electromagnets lowered from the train's undercarriage. They hover just above the rails and, without touching, induce swirling magnetic fields or eddy currents in the steel itself. Those currents create their own opposing magnetic field, pushing back against the train's motion with a powerful, contactless braking force. It's a failsafe built on pure physics, and overseeing it all is the brain. Automatic Train Control, ATC. Think of it as a digital co-pilot. It constantly monitors the train's speed and automatically applies the brakes if it's approaching too fast for the next section of track. By removing human error, it ensures safety where reaction times are measured in milliseconds. So, the wheels are self-steering, the track is rigid, and the braking is flawless. But there's another hidden layer of genius, dedicated to one thing: comfort and stability. This is the suspension system. The train's suspension works in two stages. Primary suspension sits between the axle and the bogie, the frame holding the wheels. It absorbs the harsh, high-frequency vibrations straight from the track. Secondary suspension sits between the bogie and the passenger coach. Using large air springs and dampers, it smooths out sways and bumps, giving that famously smooth ride. But at extreme speed, even this isn't enough. A coach can begin to sway side to side in a motion called yaw. To fight this, engineers added yaw dampers, horizontal shock absorbers that connect the coach to the bogie, preventing it from fishtailing. And the newest trains take it even further, with active suspension. A computerized system packed with sensors detects the slightest tilt or vibration. Actuators instantly counteract the motion, tilting the coach into curves and canceling out bumps before passengers even notice. It's the difference between a high-speed train and a high-speed luxury ride. With the track and wheels solved, engineers faced an even bigger problem: the air itself. As you push towards 400 kilometers per hour, air resistance becomes a powerful wall. Even worse, the tunnel boom. When a train enters a tunnel at speed, it acts like a piston in a cylinder, compressing the air in front of it. That pressure wave races down the tunnel at the speed of sound, and when it exits, it creates a massive, loud sonic boom that can disturb residents miles away. The solution came from biomimicry. Engineers studied the kingfisher bird, which dives from air into water with barely a splash thanks to its long, sharp beak. This inspired the Shinkansen's iconic elongated nose cones. They aren't just futuristic for looks. They're designed to slice through the air and diffuse that pressure wave, turning a boom into a quiet whoosh. But then comes the challenge of power. The pantograph, the arm that connects the train to the overhead power lines, can start to bounce or gallop at high speeds, losing contact and cutting power. The solution? Active pantographs. These aren't simple spring-loaded arms. They're packed with sensors and actuators that constantly adjust contact pressure. If a dip is detected, the system pushes the pantograph up instantly to maintain perfect contact, ensuring smooth, uninterrupted electricity. It's like a robotic arm dedicated to one job, keeping the train alive at full speed. The Shinkansen is a masterclass in engineering a system to perfection. Experimental wheeled trains have reached an astonishing 443 kilometers per hour, but that's pushing the absolute limit. To go faster, engineers had to rewrite the rulebook. Their bold question was simple: what if we could eliminate the wheel, the rail, and friction itself? The answer? Magnetic levitation, Maglev. This is not a train that rolls. It floats. And it reaches speeds that no conventional train could ever achieve. The Shanghai Maglev runs at a top operational speed of 431 kilometers per hour. But Japan's SC Maglev holds the crown, an earth-shattering world record of 603 kilometers per hour. The secret? Contact is eliminated entirely. There are two main Maglev systems. Number 1, EDS, electrodynamic suspension, used in Japan. Here's how it works. The train carries immensely powerful superconducting magnets. The U-shaped guideway is lined with coils of wire. As the train begins moving, at first still on wheels, its magnets sweep past the coils, generating electric currents. Those currents instantly turn the coils into electromagnets. And here's the magic: the induced fields repel the train's magnets. The faster it goes, the stronger the repulsion. At about 150 kilometers per hour, the lift is strong enough to raise a 40-ton carriage 10 centimeters off the track. The train is literally floating on a cushion of magnetic force. But how does it move forward? The train itself has no engine. The track is the engine. By controlling the polarity and timing of the current in the guideway coils, engineers create an invisible magnetic wave. That wave pulls from the front and pushes from the back. The train rides the wave like a surfer, limited only by air resistance and the power fed into the track. Guidance works the same way. Side magnets keep it perfectly aligned. Derailment is virtually impossible. It's locked inside a magnetic grip. Now, let's look deeper at the superconducting magnets. Normally, when electricity flows through a wire, resistance converts some of it into heat. But at extremely low temperatures, certain materials become superconductors with zero electrical resistance. That means they can generate enormous, persistent magnetic fields without requiring an endless supply of energy. The catch? Japan's SC Maglev magnets must be kept chilled to -269 degrees Celsius using liquid helium. This isn't just a train. It's a scientific marvel disguised as public transport. Number 2. EMS, electromagnetic suspension. Now let's look at a different approach, the one used by the Shanghai Transrapid. This is a system called electromagnetic suspension, or EMS, and instead of repulsion, its secret is magnetic attraction. Here's how it works. The train has C-shaped arms that wrap underneath the steel guideway rail. Inside these arms are powerful electromagnets. When energized, these magnets are attracted upwards to the steel rail above them. But here's the magic. This attraction is constantly monitored and adjusted by a high-speed control system, thousands of times per second. This system precisely manages the power flowing to the magnets to maintain a perfect, stable air gap of just about 1 centimeter. It's a constant, computer-controlled magnetic balancing act, pulling the train up just enough to float, but not enough to let it touch the rail. It can levitate even when it's standing still. And how does it move forward? The propulsion system is very similar to EDS. The track is the engine. By precisely controlling the electricity flowing through coils in the guideway, an invisible magnetic wave is created. This wave pulls the magnets on the train from the front and pushes them from behind. The train surfs this magnetic wave. Guidance is provided by another set of magnets, ensuring it stays perfectly centered on the track, locked in its magnetic path. So, we have two different philosophies, both achieving incredible speed. The Shinkansen represents the absolute pinnacle of wheeled technology, a system perfected to run at a blistering and reliable 320 kilometers per hour every single day. It's a testament to perfecting every single component: the conical wheels, the seamless tracks, the active suspension, the aerodynamic nose, to fight and tame the forces of friction and physics. The Maglev represents a revolutionary leap. Instead of fighting friction, it simply eliminates it. It is demonstrably faster, with commercial speeds hitting 431 kilometers per hour and a proven potential beyond 600. It is quieter and smoother, but it comes at an astronomical cost, requiring entirely new infrastructure built with millimeter precision. So the next time you see one of these engineering marvels, remember what you're really looking at. You're not just seeing a train, you're seeing a collection of brilliant solutions to 100 different problems. You're seeing a vehicle that stays on its track through a perfectly balanced dance of conical wheels, active robotics, and biomimicry. Or, you're seeing a machine that has transcended the track altogether, floating on a wave of pure physics. Which technology do you think is the future of travel? The proven perfection of wheels, or the revolutionary promise of magnets? Let me know in the comments below. And if you enjoy digging into the nuts and bolts of how the world works, make sure you subscribe and hit that bell so you don't miss our next deep dive. Thanks for watching.